So welcome to week 6, and I think आज the primary focus is on taking a look at a couple of examples and seeing how the approach we use to solve those problems has a direct impact on how much time it takes to find a solution to those problems. So one of the core concepts that we'd spoken about earlier when we looked at Scrabble, when we looked at other examples, was the concept of pre-work. And the concept of pre-work was that if you can do things earlier, if you can do things when you have free cycles available, that can actually help you save time when the work comes along. So for instance, when we looked at pre-encoding data, when we looked at hash tables, when we spoke about internal representation, in all of these instances, we spoke about the fact that pre-work can help simplify things. So for instance, quick question, quick test. What is this? So this is the look ahead tree from your Scrabble examples. Would you consider this as work or pre-work? And how would you qualify? How would you change your definition? What would it take? What conditions would it take for you to say, oh, this is work or this is pre-work? So question to the class. When you look at the Scrabble tree, the Scrabble look ahead tree in front of you, is this work or pre-work? You can respond in chat. You can just respond in chat. I'll treat this as an attendance quiz. So there are 35 of you here. There should be about 35 responses. Work or pre-work? What do you think? The challenge here, and that's the trick question, the question is, when are you doing this? So for example, if you're playing chess, and I don't know how many of you play chess. Chess, just like Scrabble, has an opening game, has a middle game, has an end game. And chess has a number of very well tested, very well validated opening moves that lead the game to a certain direction in the mid game and then to a certain direction in the end game. So if you're building an AI for chess, it makes a lot of sense to work through all possible combinations and see which direction the game will go in depending on how those moves are played. Scrabble though is interesting. It's interesting in the sense that even though you're building this tree, even though you're calculating these moves way ahead in advance, you're actually not sure which direction the game will go because you don't know what is the exact set of tiles that will come up. So if you think here in terms of, when we think in terms of this specific tree, the number of letters, the tiles that we are using here are tiles that haven't been drawn as yet. So we're really not sure which one of these paths would come up. And if, let's say, I'm sampling about 7 tiles from this list or 14 tiles from the bag of tiles available to us in Scrabble, we're not sure which one of those 14 tiles would actually come out. So this is a trick question in the sense that if you're doing this in real time, if you're doing this side by side with what you're doing, then it may actually be considered and classified as work. If you're doing this when the cycles are free, then it would be considered as pre-work. And this is a very nebulous definition. There's contention depending on how you've defined free cycles. There's contention on what you consider work. There's contention on whether a look ahead function is work or pre-work. A lot of interesting debate around this, but it's a good question to pose at the start of the class, so you can think in terms of what are the conditions under which the work we are doing would be considered pre-work versus work. So with this, we move on to our next example, and the next example is this one. Is this considered work or pre-work? This is your try, right? The tree that has the words that you use as a representation of the dictionary. How about this one? Is this work or pre-work? So the first one was your look ahead tree. Now we're talking about a representation tree on the dictionary. Would this be considered work or pre-work? Very good. So most of you are heading towards pre-work as far as the try is concerned, and you're very right. So now I want you to sort of take a step back and think about this for a second. This plot that you see here, this tree that ultimately allows you to search for a given word, is pre-work, because what it has done is that it has taken the dictionary. So you can take the Collins dictionary or the Oxford dictionary, and it's converted that dictionary into a format where it is a lot more efficient to search for what you're looking for compared to a simple list of words in, let's say, an Excel table or a database table. And here, I think the word that you're looking for from the perspective of computer science is you've simplified, you've reduced the search space by coming up with a representation of the data that you're working with. And the data that you're working with is your dictionary. So whether you're using the Oxford word list or you're looking at the Collins official Scrabble Players Dictionary, irrespective of which component you're using and working with, your ability to transform that into an internal representation that can ultimately lead to faster search is what allows you to deliver better results. And because you've done this ahead, you're not doing this in real time, you'll just do this once because the dictionary data structure doesn't change. There's a big difference here and here, right? So here in this chart, the one where we do a look ahead of all possible Scrabble moves, you're not sure what tiles will pop up. You're not sure what the board would look like. You're not sure what is the list of anchors on the board would look like from here to here. So as you move along the tree, you're not really sure how the game would progress. You can run a simulation to make a guess, an educated guess of what it would look like. But till that board, till that draw of tiles is realized, you're not really 100% sure on what it would look like. Here, the dictionary is stable. It's a structure. The tree data structure is mapping something which is likely to be constant. So the Oxford word list is 9,900 words. It's not going to change every second. The Collins word list is 280,000 words. It's not going to change every second, every minute, or every day. But this tree will change, right? So the nature of the element, the nature of the data, the nature of the structure that you're trying to map, that you represent, also determines how you perform work or pre-work. So in this case, work is easier because you're dealing with a constant structure. What about this one? This is your dog, right? Your directed acyclic word graph. Work or pre-work? Pre-work is key. Pre-work is key to saving time as long as you have a sense of the problem you're looking at. And as you guessed earlier, this time also, let's see who the first vote is for. Yep. This time also this is pre-work. Very good. So you have a clear sense of what is work and pre-work. Okay. If it's being done in real time, if it's being done as you move forward, if it's being done using cycles that are expensive, cycles that are going to go out and create contention for resources, then it is work. And if it's being done with free cycles, if it's being done before work is done, if it's being done in order to save real work when you're actually in the middle of a work cycle, then it's considered pre-work. Okay, perfect. So now what we're going to do is we're going to move on to our next topic. We've introduced the concept of pre-work. We spent some time on it. I now want you to think in terms of a very powerful concept that we call recursion. How many of you have heard of recursion before, or used recursion before, or worked with recursion before, prior to CS, prior to your undergrad education? So you've done it in high school, or you've done it in school, as part of your computer science education. So, okay, so a good solid chunk has done it. So now, what we want to do is we want to look at a couple of examples of recursion. And the first example that we work with is, there you go, is Fibonacci numbers. So Fibonacci numbers are, it's a series of numbers, and that has a interesting property, and that interesting property is that the number is the sum of the previous two numbers. So for example here, 1 is the sum of 0 and 1, 2 is the sum of 1 and 1, 3 is the sum of 2 and 1, 5 is the sum of 3 and 2, 8 is the sum of the previous two, 13 is the sum of the previous two, 21 and 34, so on and so forth. And this is sort of a numerical expression of what the series represents. Now, recursion, when we define recursion is a function that calls itself to solve itself. It's a function of example or instance of what we call self-reference. I don't know how many of you remember Inception, the movie. Think of Inception when you think of recursion. Now, while we use it a lot and a fair bit in computer science, it's not really a computer science concept. It's a mathematical concept. It's a concept that allows us to express mathematical problems, mathematical challenges in a form that make them easier to solve, and using what we call, the old school divide and conquer approach. And a recursive definition essentially has two parts. The first part is what we call the base case. So here, for example, the base case is Fibonacci 0 is equal to 0, Fibonacci 1 is equal to 1, and then every number after that is n is going to be f of n minus 1 plus f of n minus 2, right? So that's your, so this is your base case, and this is the relationship or the equation that we use to work through our example. So if you were to write a recursive program for Fibonacci, how would you go about and write it? You would break it down into subcomponents. So if you're solving it for n, you would first solve it for n minus 1 and n minus 2. And then if you're solving it for n minus 1, n minus 1 is going to be n minus 2 and n minus 3. Solving it for n minus 2, that's going to be n minus 3 and n minus 4. And you'll keep on repeating this breakdown till you get to your base case, which is f of 0 and f of 1. So far so good? Any questions on this? So f is a mathematical function. We are essentially expressing it in mathematical terms. We're simply saying that Fibonacci, which is represented by function f, Fibonacci of n, if you're trying to calculate the nth Fibonacci, it's going to be the sum of the two numbers, the two Fibonacci numbers before n, n minus 1 and n minus 2. So here's a very basic, very simple, very elegant, very graceful formulation for solving, for creating, for generating Fibonacci series all the way up to the number n. And this has two pieces. The first is what we call the base case. So if n is less than equal to 1, so if n is either 0 or 1, what will you return? You will return 0 or 1. Otherwise, you will return fib of n minus 1 plus fib of n minus 2. Do you now understand why it's called recursion? Because this function, Fibonacci, is self-referencing itself here and here. So now my question to you is, this is from an elegance and grace point of view, this is beautiful code, but how is this code inefficient? Why would you consider this to be inefficient? Do you think it's inefficient? So let's look at it. Let's start with a different question. I think the first question How many of you think this is efficient? We're solving this definition, right? This definition in essentially 1, 2, 3, 4 lines of code. So 4 lines of code to solve a mathematical equation sounds really cool to me. Why would somebody think or say that this is inefficient? So question number 1, first question. Do you think this is efficient? How many of you think this is efficient? You say yes or no. It's a simple call. It's like if n is less than or equal to 1, that's your base case, return n. Otherwise, return fib of n minus 1 plus fib of n minus 2. Could you explain why you think this is inefficient? So for all of you who said no, Sohaib says it's efficient. For everybody else who said this is inefficient, why do you think this is inefficient? Here's a simple look, here's a hint. A simple look at the function call, right? So if you're calculating fib of n, this is fib of n, this is your function call tree, right? So if you're calculating fib of n, what would you do? You would do fib of n minus 1 and n minus 2. And then for n minus 1, what would you do? You would do fib of n minus 2 and n minus 3. And for n minus 2, what would you do? You would again do n minus 3 and n minus 4. And then again for n minus 2, you do n minus 3 and n minus 4. And then for n minus 3, you do n minus 4 and n minus 5. And then for n minus 4, you again do n minus 5 and n minus 6. Do you see the trend? Do you see what's happening? So for example, n minus 3, how many times do you call n minus 3? So that's 1, that's 2, that's 3. 3 times you call n minus 3. How many times you call n minus 4 here? N minus 4, so this is n minus 4 here, and then here, and then here. What this tree is doing is saying that if I call fib of n, if I'm solving it for fib of n, what do I need to do? I need to generate fib of f of n minus 1 and then f of n minus 2. And then for n minus 1, what do I need to do? I need to generate f of n minus 2 and I have to generate f of n minus 3. And then what do I need to do for f of n minus 2? I need to f of n minus 3 and f of n minus 4. Does that make sense? Does that help? So what I've done is I've taken this part that you see here that I've just drawn here, taken this and I've drawn it in Excel. And I'm simply showing you that if you look at the tree, if I'm solving for n, I would need to do n minus 1 and n minus 2. And then if I'm solving for n minus 1, I'd again do n minus 2 and n minus 3. And if I'm solving for n minus 2, I'd do n minus 3 and n minus 4. If I'm doing n minus 3, I would do n minus 4 and n minus 5 and so on and so forth, right? So the tree basically keeps on growing. And the reason why we say it's inefficient is because how many times, for example, if you do f of 8, right? We take a specific example. If you do f of 8, which is Fibonacci, the 8th number in the Fibonacci series, we need to find Fibonacci f7, f6. So we'll find this here. But while we made this call here, when we make a call for f of 7, we'll again call f of 6 and then f of 5. And for f of 6 again, we will do f of 5 here. So that's 2. And then we do f of 4. And then for f of 6, we'd again do f of 5 and f of 4, right? So you see this repetitive behavior that we calling or solving for the same answer again and again and again and again, multiple times. Hence the inefficiency. So how inefficient could it possibly be? If you think in terms of the amount of work it takes to solve for, let's say, F100, how many nodes do you think there are going to be? So here for 8, let's see for 8. How many nodes do we have for 8? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. We have 14 nodes here for f of 8. How many nodes do you think we'll have for f of 100? Take a guess. There are no right or wrong answers, right? I'm just trying to help you explore how good or bad this could get. Shahid got it in 1. It's 2 raised to the power 100. So now what I've done is I've just done an initial mapping of from 100 to, let's say, 91. And then from 91 to 1, this still needs to be mapped. And you can see how many nodes are there all the way from 100 to 90. So you can just guess how many nodes will there be once you take it from 91 to 1. So here, if you count, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So with just 91, just at 91, your tree already has 36 nodes. And remember, the way that I've presented the tree is I've recombined the tree, which basically means that if I go back to my example here, there are 2 calls to f of 5. f7 has an f of 5, f6 has an f of 5, but I've merged them into a single node. And then here also there are 2 calls. f of 6 has a call to f4 and f5 also has a call to f4. I've merged them into a single node. So this representation that you saw later, this representation is a recombined tree. It's a tree that does not count 2 duplicate nodes as 2 nodes. It combines them into a single node. So the actual number of nodes here is actually going to be higher, much higher than 37 or 38 that you see. But it gives you a sense of how big the tree is going to be. The next part is how many nodes and how many calls for n and how do we calculate them. So for example, n of 0 is just a single call because you don't need to, once you hit the base case. When you call fib of n, it checks, are you less than 0 or 1? Are you 0 and 1? If you're 0 and 1, just a single call. If you're n of 2, then it'll solve for n of 1 and n of 0. And so it'll make 2 calls. And then it'll get back to an answer. And then n of 3, n of 4, n of 5, n of 6. This sort of expands, gives you a sense of if n of 8 has, let's say, 67 calls, then n of 100 will most likely have about 2 raised to the power 100 calls. Is there a faster way? Is there a better way? Is there a more efficient way that'll help us do this? Can you think of a faster way which is more efficient? How would you solve for it? So I've given you a hint here. There's a table on the right hand side of the screen, and this table has everything you need to figure out how to answer this question. So iterative, yes, but how would you go about it? You would do a for loop. Yeah, so you could do a for loop. So for example, one of the elements that we see here, one of the relationship that we see here is we know for a fact that this is a base case, and then post the base case, the second Fibonacci number is the sum of the previous 2. The third is the sum of the previous 2. Fourth is the sum of 2 and 3. Fifth is the sum of 3 and 4. Sixth is the sum of 4 and 5, right? So on and so forth. So if you could build a bottom-up calculator, a calculator that starts with the base case and then just calculates it up on the top, then there may not be a need for you to use the recursive implementation of Fibonacci. So there is a better way, there is certainly a better way, but we'll look at it a little later. Before we look at it, I actually want to look at 2 more examples of the recursive function so that you have a sense of how does recursion actually works. So the first one we looked at was Fibonacci. Now let's take a look at factorial. So you're all familiar with the n factorial function, right? N factorial is n into n minus 1 factorial. Mathematically speaking, is this a recursive definition? There's a self-reference, right? N factorial is n, the number n, into n minus 1 factorial. What about n minus 1 factorial? N minus 1 factorial is what? N minus 1 factorial is n minus 1 into what? N minus 2 factorial. And then you can keep on bringing it all the way down till you get to, let's say, 1 factorial. What is 1 factorial? 1 factorial is 1. But do you notice the structure? How familiar is n factorial to the Fibonacci number? So if you think in terms of the coding sequence, do you see the same pattern? If n is less than equal to 1, return n, and this is what? This is our base case. Else return n into n minus 1 factorial, and this is what? This is our recursive solution. If you're not the base case, then you break the problem down into smaller problems till you get to the base case. If you are the base case, then you already know what the answer is. And that's how the factorial definition of the recursive definition for solving the factorial function is interestingly fairly similar to what we just looked at with respect to the Fibonacci numbers. One more example. And if you haven't seen the similarities, how about now? This is sum of n numbers, the first n natural numbers. So if I have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 all the way up to plus n. What would the recursive definition of this look like? I've given you the code. Looking at the code, what do you think is the recursive definition? The mathematical recursive definition. Sum of n, the first n natural numbers is equal to absolutely. So sum of n is going to be n plus sum of n minus 1. And what is sum of n minus 1? Sum of n minus 1 is going to be n minus 1 plus sum of n minus 2. And what's the base case? If n is less than 0 and 1, if n is less than 1, either 0 or 1, return n, then it's 1. So sum of 0 is going to be 0, sum of 1 is going to be 1, sum of 2 is going to be 1 plus 2 is 3, and then so on and so forth, right? So I've given you 3 specific examples, 3 specific instances of using a recursive definition to solve a mathematical challenge or a mathematical function, and I think it's a very powerful, very elegant, very interesting tool that we all use. We've used it for a very, very long period of time. The only challenge is there are certain instances, there are certain variations of recursion where the implementation may actually be a bit slow depending on how the function has been called. Now the reason why we're spending this time is because we want to work through towards a specific point that deals with the concept of efficiency. So while the discussion is all about recursion right now, when we switch to how do we take a recursive function and convert that function into, let's say, an iterative function, is that worth it? Does it help us? Does it solve our challenges of time? And that's the next topic we look at.